Right, second lesson on the modulus function. We're going to concentrate mostly on solving equations and inequalities involving modulus in this lesson. But we'll further try and understand what we mean by an absolute value and have a bit more of a look at modulus graphs and how they transform. Here's our basic y equals mod x graph. Quick reminder, we have the graph y equals x for this positive part here, but then as we can't have negative values, modulus turns everything positive. We have the same distance from 0, from y equals 0, but reflected. So instead of the graph carrying on here, we still have a distance of 1 from the x-axis, but in the positive direction, and this continues through the graph. So we get this reflection of the graph in the x-axis. We can see here these two transformations. If we translate by 1 in the positive x direction, remember that that means it's x minus 1, and we can see here how the graph of y equals mod x just translates 1 in a positive x direction, and that's the equation there. This equation here is when the graph translates in a negative y direction. Remember the sign's the same when it's the y translation. That's how we write it as a column vector, and this is the effect it has. It just translates the whole y equals mod x graph down 1, and we can see on this occasion that it does actually go to negative values, but that's because the minus 1 is after the modulus part. So we're subtracting 1 after the modulus part, so we can have negative values. So how do we solve inequalities? Well, I'm going to show you two methods in this presentation, and then in the lesson I'll show you a few other methods for dealing with specific types of question. But to start with, essentially we're going to use a graphical method as described here. I won't describe it in too much detail. Have a quick read and try and understand what it's saying, but then you'll probably far better understand as I work through the examples. I will then show you a second algebraic method which sometimes also requires a graph. This is the second method. You simply square both sides. Because a modulus has the effect of turning a negative number positive, it's the distance, it's the absolute value, distance from 0, then if you square, that gets rid of the modulus signs, and we'll have a little look at how that works again, probably easier to understand by working through examples. So the first example, we're solving this inequality, mod x is greater than or equal to 2, so we sketch the graph of y equals mod x, and we sketch the graph of y equals 2. If we do that here, we can see we've got there y equals 2 and here y equals mod x. We're looking at where this part of the graph is greater than or equal to 2. So in other words, where this graph here is above, has a bigger y value for any given x value than y equals 2. And we can see here that from this point, y is greater than 2 on this graph, and from this point in the negative direction, y is greater than 2. So we just need to know what the points A and B are to define these two regions. Greater than or equal to B, B's x value, and less than or equal to A's x value will be the two regions. Well, B is probably the easiest. We know that the y value at B is 2. Because it's on the line y equals x, the x value must be 2 as well. And then we can simply use the symmetry of the graph. We know that it's a reflection in the y-axis. So we know that this distance here is the same as this distance here. So the y value at A is 2, so the x value must be minus 2. So we end up with x is less than or equal to minus 2 and x is greater than or equal to 2. Note at this point that this is equivalent to saying that x squared is greater than or equal to 4, which is relevant as we're about to see. Right, looking at a more difficult one involving modulus of both sides. We've got the modulus of x plus 4 is less than the modulus of x plus 2. Again, draw the two graphs. We're looking at where the graph of x plus modulus of x plus 4 is below, has a smaller y value than the graph modulus of x plus 1. So we can see that y equals modulus of x plus 4 is above y is the modulus of x plus 2 here, but from here onwards in the negative direction it's below, isn't it? So again, it's this x value here we're looking for to define the region. You can probably just do it by symmetry. You could just look at the graph symmetrically. Well, it meets at minus 4 and minus 2, and this point here is clearly in the middle. These are both just translations of y equals mod x, which is related to y equals x, isn't it? So for each one it goes up, it will go across 1. So we can tell really that this is going to be the point x is minus 3. If we use the second method, we square both of these terms ignoring the modulus. So we go to this. We go from modulus of x plus 4 is less than the modulus of x plus 2 to x plus 4 all squared is less than x plus 2 all squared. Looks a bit horrible, but actually when you square out and you start taking terms over, you'll see it simplifies quite nicely. Subtract x squared from both sides. Subtract 4x from both sides, leaves just 4x on the left, and then subtract 16 from both sides to leave just x term on this side, and we end up with 4x is less than minus 12. Divide both sides by 4 and we get x is less than minus 3. Looks like quite a nice, neat, easy method, and it certainly is for these type of questions. A little bit more complicated if we end up with a quadratic, as we may then need to look at a graph to see where the region or regions are that we're dealing with. So method 1 can be more reliable. Okay. This time we've got a modulus on one side and a number on the other. We're using the graphical method, so we sketch the graph x minus 2, modulus of x minus 2. So y equals the modulus of x minus 2 is this graph here. We draw y equals 1. And we're after where the modulus graph is greater than or equal to 1. So similar method to the first example. We can work out the value of x at b. We know that y equals x minus 2. We know that y equals 1. So if we put that in there, we can work out that x must be 3. We can then just use the graph symmetry again to work out that this value must be x equals 1. So the regions are x is greater than or equal to 3 and x is less than or equal to 1. Okay, for our final example, we'll look at a graphical solution where it isn't quite so easy to work it out from the graphs because the symmetry doesn't make the results as easy to spot. here, so we want these x values here between these 2 points, and not including, because it's not less than or and equal to, it's just less than. Well, to find out the x value at B, we look at where the two positive bits of graph meet, so we can just get rid of the modulus signs for that. It's fairly easy. Expand out the bracket, we get 3x minus 3 equals x plus 1. Subtract x from both sides, we get 2x. Add 3 to both sides, we get 2x equals 4, x equals 2. So x equals 2 here, and that was fairly straightforward because we're looking at the positive bits of these graphs. To look at the x value at A, we're still looking at the positive bit of this graph, so we're still looking at the graph y equals x plus 1. In other words, we're looking at the reflection of this graph in the line y equals x. So it's a reflected part, so we need to, when we reflect in the x-axis, we turn everything negative, don't we? So we change this here to minus the whole thing. And if we're minusing the whole thing, then we end up with this. Both signs change, don't they? So this would be 3x minus 3. It becomes minus 3x plus 3. Work it all out, expand out the bracket, and we get 4x here because we add 3x to get rid of the minus 3x, and then subtract 1 from this side and from this side, and we get 2 equals 4x, x equals 2, x equals a half rather. So we end up with a region between a half and 2. So a half is less than x, which is less than 2, because remember we're dealing in a pure inequality here, not and equal to. Okay, your turn. Use both methods and have a go at these to make sure you understand it. If you're successful more or less with the first 3, then you're ready to go on. I'd expect you to get at least 2 of the first 3 right, but certainly to get close. Tolerate 1 or 2 small mistakes, but really you should be getting those first 3 right. The fourth one's a bit more difficult. You might need to use the graphical calculator and G-solve or the equation solver, but have a go at all 4. Pause the presentation and then have a look at the answers.